When we look at a honeycomb, we are instantly struck by a quiet, unsettling realization. There is a haunting geometric perfection here, a design so precise, it feels deliberate. This is not an aesthetic coincidence. The structure of the honeycomb is perfectly, ruthlessly optimized to store the maximum volume of honey using the absolute minimum amount of space and material. But how? How do these tiny, fragile insects possess such terrifying engineering prowess? Is it a whisper of divine architecture, or is it something much colder, much more mechanical? To truly understand this riddle, it's time to go down the rabbit hole. This mystery has haunted human intellect for millennia. In 36 BC, the Roman scholar Marcus Terentius Varro proposed a daring hypothesis. He suggested that the hexagonal shape of the comb was the ultimate way for bees to build their fortress with the least amount of precious wax. But Varro only had intuition. He didn't have the proof. It took humanity over 2,000 years to finally confirm his suspicion. In 1999, mathematician Thomas Hales officially proved what we now call the Honeycomb Conjecture. The math was definitive. The hexagon is the absolute pinnacle of spatial efficiency. But to understand why, we have to look away from the bees and look at a toy. Consider the soap bubble. We intuitively accept its spherical shape. But have you ever stopped to ask why bubbles aren't square? Why aren't they triangular or jagged or irregular? The answer lies in one of the most fundamental laws of our reality. Physical systems always seek the state of lowest free energy. In simple terms, it takes far less energy for a bubble to exist as a sphere than as a cube. The air inside and outside exerts constant pressure on the delicate membrane of soap and water, while the molecules of the liquid naturally pull inward, trying to shrink. To resolve this conflict with the least amount of effort, to minimize its surface area and conserve its energy, the bubble has no choice. It must become a sphere. But how does a floating sphere explain the flat walls of a honeycomb? When bees begin their construction, they secrete liquid wax. Because of the cylindrical shape of their bodies, they naturally mold the openings as circles, and mathematically, this makes sense. The circle is the ultimate shape for a solitary structure. In geometry, this is known as the isoperimetric problem. Imagine you have a piece of string exactly 1 meter long. If you want to enclose the largest possible area on a table, you must form a circle. If you try to make a square or a triangle with that same string, you will enclose less space. The circle is the state of lowest free energy. So why aren't the chambers of a honeycomb circular? Because circles do not like to share. When you pack circles together, they leave empty, wasted spaces between them. These are called interstitial voids. In a hive, these gaps are a death sentence. Because the wax is fluid and possesses surface tension, just like the soap bubble, those empty voids would be filled with excess wax. This means more material, more weight, and a massive waste of precious energy. To eliminate these voids, the plane must be tiled. And mathematically, only 3 regular polygons can do this without leaving gaps: the triangle, the square, and the hexagon. But remember, standing walls are expensive. Creating them costs energy. To minimize the total free energy of the system, physics forces the geometry to adopt the smallest possible wall area for the volume being stored. The hexagon is that golden ratio. It is the state of stable equilibrium where the interface energy is at its absolute minimum. Any other shape would require more walls, storing more tension, and leaving the system in an unstable, high-energy state. There is no conscious mathematics here. There is no genius architect. only the blind, beautiful inevitability of the laws of physics. Bees construct circles. The universe crushes them into hexagons. This hexagonal signature, dictated by the ruthless laws of thermodynamics, is written all over our reality. If you zoom in on the compound eye of a dragonfly, you will find a perfect mesh of hexagons. Each lens, or ommatidium, is tightly packed. If they were circular, there would be blind spots between them, reducing the insect's survival rate. The hexagon grants 100% visual coverage with the lowest biological cell cost. Deep within our own chests, the alveoli in our lungs arrange themselves in the very same hexagonal patterns to maximize oxygen exchange. Even in the cold, dead basalt columns of the Earth, where lava cooled and contracted, the rock cracked into hexagons to relieve its internal physical tension in the most efficient way possible. The hexagon is not a beautiful geometric shape. It is a thermodynamic scar. It is the mark left behind when the universe is trying to survive on the lowest possible budget of energy. And in our world, the universe always wins.